My name is Phi, together with my colleague Disyu. Today, we would like to present the DAGOBAH, an enhanced scoring algorithm for scalable annotation of tabular data. This work is a collaboration of Orange, a French company, and EURECOM, a French university. First, I would like to point out why we want to annotate the tabular data. Here, I highlight three areas that DAGOBAH can make a contribution. The first one is data science. DAGOBAH wants to provide tools to clean the table, understand the meaning of each field. The second one is data governance, where the annotation enables intelligent indexing and manipulation of the data. The last target is knowledge enrichment, where the knowledge from massive volume of table can be used to enrich the knowledge graph. An example we show here. The current knowledge graph meets the location information for the film French Dispatch. However, this information is available in the table. So DAGOBAH can extract the information to enhance the knowledge graph. And eventually, the enriched knowledge graph can be used by a virtual assistant to give better answer for the question related to the film French Dispatch.
But how can we achieve this goal? And let me introduce our DAGOBAH system. And this system is basically composed by 5 major steps. The first one is to do the entity lookup, which aims to select candidates for each cell of our table. And the second part is to do the candidate scoring, in which we will give each of our candidates a confidence score. And then we come to our annotation. The first annotation is to identify the relationship between 2 columns. And second, we will do the entity linking to identify an entity who can represent a cell of our table. And finally, we will try to identify a type for each column.
The first step in the annotation workflow is entity lookup in the knowledge graph. We are retrieving for a table cell the relevant candidates whose label or alias are similar to the cell. In the context of the challenge, the corpus is very large, with thousands of tables. To be efficient, we have built our own lookup service in a big data platform. Specifically, from a raw data dump, we use the Wikidata toolkit to filter the dump. We only keep the QIDs, PIDs associated with the label and alias in all languages. And at the end of this step, we have 87 entities. We store them in the Hadoop distributed file system. We show here 3 partitions we store the entity. And now to do the lookup, we use the Baseball framework. We consider Levenstein distance to evaluate the similarity between the table cell and the entity. And for example, in the table in the left, a misspelled mention title corporation might correspond to entity title corporation according to the Levenstein distance. And we also show the lookup time for 1,000 cells. And we can see with 150 machines, it takes about 17 minutes to finish, means 1 second for a cell, which is efficient.
And after having our candidates before the annotation step, first of all, we aim to give each of our candidates a confidence score. And this score is mainly depends on the candidate's string similarity between mentioned cell and whether the candidate's neighboring nodes are related to the context of the table. Contest scales will adapt different strategies according to different scenarios. When dealing with string scenarios, we use Levenstein similarities, and when dealing with mathematical scenarios, we use SMAP equation to give contest score. For example, in this table, we want to annotate the cell Sega. So we compare the label of each candidate with Sega, and we compare the cell in the same row of the original mentioned cell and the neighboring nodes of our candidates. We have 3 candidates, and we will calculate the score for each candidate, and then we will send those scores to the next step.
Okay, for column property annotation, this task is to find a semantic relation between a pair of other columns. In other words, we try to figure out the more relevant relation among the ones connecting candidate entity in head column to candidate's entity in tail columns. To do this, we employ majority voting, which rely on the occurrence and accumulated score of the relation. For example, in the table in the right, we consider the first and the third columns and the relation P740. This relation can connect a Sega candidate to a Tokyo candidate and a title corporation candidate to Tokyo candidates as well. So the occurrence of this relation is 2, and its score is the sum of the two scores corresponding to Sega Tokyo and title corporation Tokyo. But we might have a question, that is, how can we know a relation can connect a head to a tail? In contrast to the head, which is always in ID, the tail can be ID, that's number, day. So we use different matching strategy. Can be an ugly distance for the number or Levenstein distance for string. And finally, the CPI relation is the one with highest occurrence. If there are many, we choose the one with highest score. And for cell entity annotation, CEA, this task is to annotate the table cell with entity of a knowledge graph. Example, we want to annotate the cell tag Sega in the table. And from scoring algorithm, we already have the score for all candidates. Now, taking the CPI relation into account, we update the score of each candidate by adding 1 if the CPI relation can connect this candidate to its counterpart in the tail column. For example, in the table, we see the CPI relation P740 can connect the candidate Sega Japanese company to Tokyo, and then we can update the score for these candidates. Finally, the CEA is the candidate with highest score.
And the last part of our annotation system is column type annotation, which is called CTA. Our CTA annotation is basically based on majority voting on types of outputs from CEA outputs. Among them, we have also applied different technologies to improve our accuracy, coverage, and specificity, which includes, first of all, type enrichment, in which we considered type hierarchy with 3 levels. Level 0 for the direct types and level 1 and 2 for the insistence of distance 1 and 2. We do this is because direct types are preferable in case of some vote. If it still can tell the result in this case, a study of distance to scene is adopted. We will calculate the relative longest path to scene for final candidates to extract his level of specificity, and we will select the most detailed candidate. For example, in this table, we have already extracted our CTA outputs, and we list all types of those outputs, and then we will calculate the sum of each type, and we will choose the highest one, which is a company of games. And for evaluate our project, we have participated in the challenge SemTab 2020. The result is shown in this figure. From a macro perspective, we have achieved a good result. Our accuracy rate is in the first echelon and is very close to the winner of this challenge. And I also want to point out that when in the round 1, we didn't completely upgrade our lookup system. so the relative accuracy rates will be lower. And we try to examine our system from an objective perspective and analyze its advantages and disadvantages. For polls, first of all, we have a high coverage and our calculation is efficient, which means that we can apply it in the distribute system and is optimal in high quality tables. But for cons, we suffer from KG version difference issues, and our algorithm is largely depends on tables quality. And we also have problems about the flexibility. And talk about our future works. First of all, we would like to do more studies on more table layouts by adding and pre-processing steps in our workflow, which aims to figure out some major features about the table, like the orientation of the existence of header. And we also wish to try to do more studies on the real context situations which we have incompleteness of our knowledge graph. And we also wish to do some researches based on embeddings, which we plan to do the graph embedding and table embeddings and do more experimentations to figure out how to do the disambiguation. And we would like to tackle the dynamicity of evolving knowledge graphs. And last but not least, we would like to build an end-to-end annotation system, including available APIs and GUI. And thanks for your attention.